Good morning or good afternoon or good evening, everyone, depending where you're connecting in from today. Thank you for taking time out of your day today to come listen to us talk. Today, of course, we have several guest speakers. We have ST as well as Percepio, and today we're going to be talking about how to develop extraordinary user experiences on the STM32MP1 by using performance analysis, both from internally within Storyboard's embedded GUI development tool, as well as Percepio's Tracealyzer. So today's session is being recorded. So just to let you know that if you do have any issues or maybe need to drop off, or perhaps you have a colleague that would benefit from today's topic, we will be making this session available on demand, and so it can be accessed at any point in time. Also, we are streaming across the internet, so if you do run into some maybe audio issues or connection issues, try just refreshing the window, and that usually resolves about 80 to 90% of those particular issues. Also, because we have live panels today, we will be doing Q&A at the end of today's session. So what you'll find within your window is a Q&A tab where you can easily go in and pose your questions to all the guest speakers. As well as, if you haven't already, feel free to follow us on social media. We are active on Twitter, LinkedIn, and Facebook. We use the hashtags GUI development as well as Crank Storyboard, so you can find our great social posts using those, or feel free to interact with us. Today, like I said, we have a lot of great guest panelists. We have from ST, Mike Hartman, who is the product marketing manager for MCUs and MPUs at STMicroelectronics. We also have Johan Kraft, who is the CEO and founder of Percepio, and along with Johan is Christopher Martinson, who is a field application engineer with Percepio. And then, of course, we have from Crank Software, Gary Clarkson, who is a field application engineer, and myself, Scott Snyder, who is the product marketing manager at Crank Software. So before we jump into things, just a quick overview of today's agenda. We're going to start things off with an overview on the STM32MP1 platform, going into all the great things about it. And then we switch things up. We're going to go into Percepio and do an overview of Percepio and Tracealyzer. And then, of course, we'll hand things off to me, and I'll talk about who Crank Software is and what Storyboard is. And then we'll dive into the integrated tools that are designed to really help you optimize the performance as well as the experience of your embedded GUI applications, and as well as a demo on how Tracealyzer really greatly simplifies that system level performance analysis of your embedded GUI applications, and in particular for the STM32MP1. And then we'll wrap things up with your questions. Going to hand things off over to Mike, who will be kicking things off and talking about all great things STM32MP1 related. Mike, over to you.
Thanks, Scott. As an introduction, I'm Mike Hartman with ST's microcontroller and microprocessor product marketing team. I'll provide a brief overview of the STM32MP1 microprocessor and some potential use cases for embedded graphics applications. The STM32MP1 is a general-purpose microprocessor that can address various applications, from industrial to medical and consumer products to home appliances. From its inception to its introduction onto the market, the STM32MP1 was based upon the strong foundation of our STM32 microcontroller products. This includes our best-in-class support, tools, and ecosystem. Furthermore, ST's supply chain and our 10-year rolling longevity commitment enable you, our customers, to design products that will have a long, successful, and profitable life. The STM32MP1's flexible architecture addresses Linux and real-time processing, including graphics-based HMI applications. And lastly, with our mainline OpenST Linux distribution and our support for STM32Cube, your project's software development can be accelerated. Furthermore, by leveraging authorized partners in ST's partner program, you can reduce your overall time to market. For those of you not already familiar with the STM32MP1, let's take a look at the top-level architecture. On the left side are the dual Cortex A7s, providing up to 3040 DMIPS of performance when clocked at 800 MHz. This high-performance domain is where Linux or Android would run. The optional 3D GPU in the top middle provides OpenGL-compliant hardware acceleration for advanced graphic user interfaces. And on the right side is the Cortex M4, providing up to 260 DMIPS of performance for time-critical or other offloaded functions. This real-time domain can run bare metal or an RTOS. The STM32MP1 supports DDR3, 3L, LPDDR2, and LPDDR3, and a wide range of non-volatile memories. There are ample interfaces for connectivity as well as a rich analog integration. Additionally, ST offers the STMicroelectronics, a power management IC designed specifically for use with STM32MP1 based platforms. Now that you have an idea of the STM32MP1 architecture, let's take a look at some possible applications. Perhaps you are designing an advanced gateway product, maybe a device used for home security, HVAC control, or home automation. The STM32MP1 can address the critical features needed for these applications. With the dual Cortex A7s clocked at 800 MHz, the STM32MP1 can support 720p HD video decode. When using the STM32MP157, with the optional 3D graphics core enabled, you can implement a high-performance user interface developed with Crank's Storyboard tool. And the heterogeneous architecture with both Cortex-A and Cortex-M cores provides the flexibility needed for various applications, including audio, voice, and real-time processing. Artificial intelligence is all around us these days. The STM32MP1 architecture and ecosystem enables AI capability such as image classification, voice recognition, or predictive maintenance in any end application. Perhaps you would like to add AI to your STM32MP1 project. Since the STM32MP1 has two different cores, there are two approaches that you can take. First, using the Cortex-A subsystem, we have support for TensorFlow Lite. This is achieved through an artificial intelligence expansion pack for OpenST Linux. This package contains AI and computer vision frameworks and application examples. Further information can be found on wiki.st.com. Looking at the Cortex-M real-time subsystem, we support STM32Cube.ai. Available for many STM32 microcontrollers, STM32Cube.ai can also target Cortex-M4 in the STM32MP1. STM32Cube.ai allows you to map and run pre-trained artificial neural networks in the real-time domain of the MP1. And over the last year, we've seen more interest in non-touch-based human-machine interface. Whether it is an AI-based gesture recognition or voice command and control, the STM32MP1 architecture and ecosystem provides you with the tools needed to implement the solution. At ST, we understand that starting a complex STM32MP1 project isn't always as easy as buying a dev board and starting to write code. We believe that there is enormous value in our internal and external ecosystem. The tools and software releases from ST are critical, but the adoption and support from partners like Crank Software and Percepio are just as, if not more, important. If you have any questions about the STM32MP1, I'll be available at the end of the webinar during the Q&A session. At this point, I'll hand it back over to Scott. Thanks a lot for your time. Scott, it's all yours.
Thanks, Mike. And I'm going to pass things over now to Johan to provide his introduction of Percepio and Tracealyzer.
Okay, thanks, Scott. I guess you can see my screen now. Percepio is a Swedish company and also an ST partner, focusing on visual trace diagnostics for developers of embedded and IoT software systems. We have two related products, Tracealyzer, intended for development use, and DevAlert, which is for monitoring of system testing and deployment. So I'm Johan Kraft, the CEO and founder, and with me today is also Christopher Martinsson, a field application engineer at Percepio, who will later provide a demonstration of Tracealyzer on a Crank Storyboard use case on the STM32MP1 on Linux. So Tracealyzer is our solution for visual trace diagnostics, helping developers of RTOS and Linux-based embedded systems to become more productive and develop better products at a lower cost. You know, most embedded software today is multi-threaded in one way or another, using Linux or an RTOS. And for multi-threaded software, the application source code doesn't give you the full picture of the runtime system. It can be seen a bit like a black box, or even the dark side of the code, if you will. It's practically impossible to predict exactly how the code will behave as a full system if you only look at the source code. So visual trace diagnostics gives you a visual timeline of the software in real operation, together with a large set of visual overviews, metrics, and statistics. This makes it far easier to debug issues found when running the full system, which otherwise can be quite difficult and time-consuming to resolve. You can also analyze and improve the software design for better reliability and performance. With a solid software design, you get a deterministic behavior with fewer bugs and better testability, speeding up development and improving quality. Visual trace diagnostics also makes it easy to measure timing and performance metrics for verification of real-time requirements and for tracking the software performance throughout the development project. Empowering developers with this level of insight brings considerable business value in terms of higher development productivity and shorter time to market. And with better insight, developers can make the software run much more efficiently, which can allow for selecting more cost-effective processors with lower energy usage. This way, you can increase battery life and even reduce materials costs. So what is visual trace diagnostics, and how is this related to software tracing in general? Well, visual trace diagnostics builds on software tracing. It's used for tracing is what we're using for data collection. This way we can record the software behavior during operation. But a general challenge with software tracing is the sheer amount of data produced. And since software is typically quite repetitive, you mostly get repetitive or irrelevant repetitions of the same patterns. It's typically the anomalies you're interested in, but often you don't know exactly what to look for. Basically, you can't see the forest for all the trees. To address this and really benefit from software tracing in everyday development, you need two more components. The data needs to be processed into a meaningful model that allows advanced analysis and visualization. This requires the solution to actually understand the software events, not just their name, but what they actually do and how that affects the system state. With such a model, the software trace can be visualized from many perspectives and on different levels of abstraction. That makes anomalies stand out and provide quick, intuitive comprehension, even for very large datasets, long traces. The human brain is visual and excellent at pattern recognition, especially at spotting anomalies in repeating patterns. And we can leverage that by showing visual overviews from different perspectives, such as graph over CPU load or task response times. Finally, by connecting these views, we allow for a top-down workflow that is ideal for system-level analysis. You can spot anomalies and strange behaviors in high-level overviews and then drill down to inspect the details and see what really happened. And this is what we mean by visual trace diagnostics. And this is useful for debugging purposes whenever you need a timeline of your software. And that's not only for performance measurements, but whenever you're interested in the order of important events. And this is often the case when debugging a full multi-threaded system, and especially important when the location of the bug isn't obvious from the symptoms, or when the issue is difficult to repeat. Maybe it only occurs once in a while for no apparent reason, or in cases where you can't use interactive halting source code debugging that stops the system because you might have real-time requirements from connected equipment, etc. With visual trace diagnostics, you can reduce debugging times significantly and get more time available for customer value creation, so to say. And with better ability to solve complicated bugs, you reduce the risk of project delays or having to work 100 hours per week to make that deadline. And with better insight during debugging, this means less guesswork, which is likely to improve software quality as the bugs can be fixed properly. Another really important use of visual trace diagnostics is to analyze and improve the software design. Many of you have probably learned the hard way that designing multi-threaded embedded software is quite challenging. And there are best practices that are crucial for making deterministic, reliable, and efficient software. And it's really important that all involved developers and all parts of the software or the code follows these best practices. Some things are quite easy to spot in the source code, but anything that is even remotely related to software timing or scheduling and shared resources requires measurements in runtime. And visual trace diagnostics makes this much easier. You can reveal deviations from best practices that are typically risky or inefficient solutions. For instance, if you have a lot of interference between the threads or chaotic variations in software timing that may affect the order of important events and thereby reduce testability. And this with testability is really important because a poor design with a chaotic runtime behavior will basically mean that your test coverage will be more or less random, especially with respect to timing sensitive bugs like race conditions and deadlocks. And that increases the risk of elusive bugs in production code. So software design is really important for quality testing. So it's important to keep track of the software design throughout the development. Otherwise, you might find yourself in debugging hell, basically, when the application grows. And this may require a major redesign of the software to get stable. The earlier you can detect such issues, the fewer changes are required to fix them. With Tracealyzer, you can analyze the initial software design to ensure that you have a solid foundation for your application. And you can keep track of changes during the development and spot new issues as early as possible. And by ensuring that your design follows best practices, you can reduce the amount of bugs and improve the effectiveness of your testing. This can also improve software efficiency, since you can reduce the amount of processor time and memory needed for the application, and that can allow for using a more cost-effective processor and also improve battery life. The third major benefit of visual trace diagnostics that we will look more into today is that it becomes far easier to verify software timing and performance and keep track of such metrics throughout the development project. So you can ensure compliance with real-time requirements and see that you have good software performance, and also find new ways to improve the performance. There might be a lot of low-hanging fruits, things that are easy to change, for a much more responsive and capable product. By enabling early detection of such issues, you can avoid last-minute panic, costly project delays, and customer dissatisfaction. As of today, Tracealyzer supports embedded Linux using the LTT-NG tracing framework. This can be used on OpenST Linux, for instance, as well as several leading real-time operating systems like FreeRTOS, Azure RTOS, and VxWorks. And with that, I would like to hand over back to Scott. Thank you.
Thank you, Johan. With that being said, let me jump into the embedded GUI side of things. And definitely when it comes to developing GUIs for today's products, things have become increasingly more challenging, right? The user experience has really become one of the defining part of today's consumer products, with the UI being one of the main factors that is driving the value that consumers actually see in the product themselves. Like, consumers are not concerned about the size of the device or the fact that it's being powered by maybe a smaller MCU hardware. They look to their smartphone that they have in their hands, which provides that kind of level of touch experience, and they expect that these embedded products still have fast, engaging interactions that are informative in a non-cluttered navigation. So, different form factors, often require a different approach to UI development, such as varying sizes and shapes and hardware and displays, requiring different types of user experiences or interactions than the traditional larger rectangular ones. And last but not least, because a lot of embedded devices are becoming more portable, it's important that the experience to be optimized for these portable devices, so that way they consume less energy from the battery that is powering them. And so, what it comes to is the founders of Crank Software set out to build a solution that could really help remove the inefficiencies that frustrated them and their developer colleagues when it came to developing UIs for embedded devices. Storyboard was designed to remove the barriers and issues that are typically associated with UI design and development. It was purpose-built for collaboration around the user experience, so designed specifically to help developers and designers work together closely and iterate with ease in the quest for the optimal end user experience. Also, it has a distinct separation of design and code environments. So really kind of taking the front end UI design, decoupling it from the back end logic, enabling developers and designers to build the UI, to update and test the app at the same time in parallel without destroying each other's work or disrupting the overall development process. Also, rapid design iteration and re-import technologies at the heart of Storyboard. So allowing designers to take PSD or sketch files, import them into the solution. If they need to make changes to design, easily re-import them back in the solution without taking down any of the actions or events that were previously established or attached to those assets. And then last but not least, we have a graphical comparison and merge tool that really allows the development team to remain in control of which change content you wish to accept and deploy before committing those changes to the final design. If you haven't heard about Crank Software before, I can guarantee that you have seen or probably interacted with a product whose UI was built using Storyboard. Our technology was really created to help, like I said, make UI development easier for embedded platforms. So whether it's traditional markets like medical, automotive, or industrial, or consumer markets like wearables or white goods, they all share the common challenge when looking to deliver an excellent user experience on that product's LCD screen. So who is Crank Software? We are both a software and services company. So what that means is we have Storyboard, which is our product, our software product, but we also have professional services that are there to help you out, that if you have a project but not maybe all the available resources to help build that project, our professional services team are here to help you out. Our leadership team has extensive background in embedded graphics and systems, and we have a large global customer footprint that are from Fortune 500 to small organizations. So no customer is too large or too small for us to work with and really help excel their UI development for them. Plus we have millions of devices or millions of UIs in devices that are out there in the field. Plus we have a large global distributed partnership that really makes it easy for you to get support in your local language, in your local region as well. So with that being said, how can Storyboard help? Well, you know what? Powerfully simple yet sophisticated is what our customers tell us. It's easy to use interface really enables them to create UIs more quicker and more efficiently. So this decoupled front-end UI development from the back-end logic really allows designers and developers to work in parallel to build the GUI application for the device. And that's why Storyboard's development architecture really makes it easy to get started early on the UI development, really makes it easy to embrace design iterations, and of course helps reduce the complexity of developing GUI applications in a market that constantly sees evolving embedded hardware, or maybe within your organization a series of product lines, really allowing you to get to to build that UI quicker, so you can get that product to market faster and in a more efficient manner. So how is this done? Well, like I said, the UI development can begin within a familiar UI design tool such as Photoshop or Sketch, and when ready can be easily imported into the Storyboard application where those different assets of the design become the building blocks of the UI. From there, the UIs can be brought to life using Storyboard's integrated animation tool, allowing you to create, edit, review animations all directly within Storyboard. Plus, any critical UI flow and usability testing can all be performed within Storyboard using its integrated prototype and simulation functionality. Again, all without requiring the final hardware decisions to be made or without having to deploy it onto the actual hardware to test this out. But of course, the sooner you can get the hardware, the sooner you can really kind of take the complexity out of the solution and really kind of iron out those wrinkles. Once development begins, though, designers and developers can easily fine-tune the UI based upon whether it's internal feedback or maybe it's hands-on testing with customers. And these product changes can be implemented without impacting the development progress or causing a complete teardown of code. So the UI can be completely modified if want, and simply re-imported from Photoshop or Sketch, allowing without having to create an entirely new application or, like I said, overriding prior development effort. And then you can remain in control of those iterations through our unique graphical and compare merge tool, which allows you to choose which changed content you wish to accept and deploy or reject within the UI before committing those changes to the final design, really allowing for a more efficient and collaborative workflow process, in particular when you have multiple people that are involved in the overall UI development process. And then, of course, you can use actionable insight to really assist with the development decisions as the UI is being developed. So through our performance and optimization tools, which Gary will talk about in a moment, you can really monitor the resources directly within Storyboard, so you know with confidence that your UI performance is optimized for your target hardware. And then last but not least, with the vast choices of hardware and operating systems that you can get from ST, it's good to know that a Storyboard UI can run on it. And that's because we've taken the heavy lifting, and what we use is runtime engines, which allow you to take that UI that was built and kind of move it from maybe one of the STM32 MCUs and up to the STM32MP1 without having to completely rebuild the application. And therefore, it really helps de-risk your embedded device project by introducing a framework that can easily support technology and design changes at any point in the development cycle, which really allows for UI flexibility. And what I mean by that is you had your scalability, which means you could easily scale up to the more powerful MP1, or maybe scale down your footprint to a STM32 MCU device to take advantage of maybe the low power consumption hardware. It also provides you that portability, like I said, that you can adapt to changes in your technology stack, whether it's hardware or software OS altogether, or maybe take advantage of the specific board features such as proprietary graphic libraries, maybe 3D hardware acceleration, etc. And then you have that reusability aspect of it, which allows you to kind of build that UI once, but then you can use it across different product lines for that consistent brand look, touch, and feel, allowing you to save time on development. And so with that being said, instead of me talking, I'm going to kind of pass things over to Gary, where he is going to take you through a live walkthrough of the actual hardware itself. So let me just kind of share things with Gary right now. All right, over to you, Gary.
Thank you, Scott. Quick introduction. I'm Gary Clarkson. I'm an applications engineer for Crank Software. My role really is to help customers evaluate hardware and get up and running with Storyboard as fast as possible. So what I'm going to talk to you today about is some of the challenges we have out in the field with customers getting up and running with their applications. So I wanted to take you through a couple of scenarios. One scenario in particular is frames per second, and we're going to be doing that using the STM32MP1 hardware platform, and we're going to be running that with Linux and taking some snapshots and investigating it in a lot more detail with the Percepio Tracealyzer tool, which is truly awesome. So let's first talk about how Storyboard helps. So as we said earlier, the whole tool really is aimed at accelerating development. So the idea is to get this change, modify, try cycle to be much more efficient. In terms of embracing iterations, you're able to develop on the desktop, and I'll show you how to do this. We'll take one of our samples and we'll deploy it to the target in real time. So this is the iterative part of the story. So this helps you try something, test it. And we really like to encourage customers to develop and test on hardware as often as possible and as quickly as possible. So it's only when you really see how something performs on the real hardware that it gives you a proper perspective of the application. So in terms of UI flexibility, well, we'll show you how the UI is separated from the back end. So in a little bit more detail, Storyboard is somewhat different to other solutions. We use what we call a model view controller architecture. And in this architecture, we're able to develop things on the desktop using a runtime targeted at, for example, a Mac or a Linux or a Windows 10 environment, and then deploy to a target. So in this case, we're looking at the ARM Cortex-A7 based runtime, which is going to be running the STM32. So these two are basically separate domains, and not only do we separate the kind of UI from the code, so we don't generate code, we generate a model, and our model runs on a runtime engine. But also the UI itself is separated from the back-end code. So here, what we mean by UI is basically the customer behaviors, the UI, the presentation of data, collection and interpretation of events and triggers. And the back-end in our case is we're going to be using an automotive style of application. The back-end would be data collection, processing, analysis, and then basically presenting those data, that information from a state machine, from a controlling engine, whatever it is that the device is doing, and presenting that to the UI for representation. So the two are actually separated, and this allows you to develop and test on a desktop and just exchange events with the target, or indeed running as two separate processes on the target. So in our case on Linux, we're going to be using a back-end process written in C or C++, and a front-end process which is running the Storyboard engine, the SB engine, and one of our models. Those two communicate by using what we call channels. These are event queues or event channels. These allow you to exchange messages from the front end to the back end and from the back end to the front end. So it's a physical and logical abstraction. In our case, these are IPC messages into process messages, so two separate PIDs on Linux. They're communicating using a queue mechanism called Storyboard IO, and this wraps a platform dependent kind of message exchange architecture. For this example on Linux, we're using sysv message queues. So we'll be able to show you a bit more detail about how that works, but essentially you're sending and receiving events backwards and forwards. And this is a very simple API, and we've got a simple test app to emulate some of those data messages. So first, a few words about frames per second. We get a lot of inquiries and a lot of customer debate and discussion around how many frames per second. I want to know, how many you can do. So the answer is it depends. And the reason it depends is because it's about the rendering technology itself. So Storyboard uses an intelligent on-demand rendering engine. So if there's nothing to change on the UI, we're not going to change the UI. So we don't do a frame update. We don't do a kind of a write to the frame buffer. until there's something to change. So we internally process the instructions and the intent for that UI, and we will not display a change if there isn't any. So that allows us to cut back on CPU loading and all that sort of stuff. So this is basically intelligent on-demand rendering, and this is a difference between display refresh, which happens every 60 frames per second or whatever refresh rate the UI is, the physical hardware is doing, versus display update, which is when something changes. And the frame buffer effectively is just a block of memory, and there are many memory kind of architectures, and when using a GPU, for example, this is controlled by OpenGL. So the OpenGL drivers control the frame buffer and also the acceleration, and we'll be using those in our API. So we're handing off some of the drawing efforts to a GPU. So this is blitting and blending and merging and that sort of stuff. So I thought I'd explain that. So frames per second is not all it's made up to be. In practice, all you have to do is display the frames updated as fast as you need, and that is application dependent. Okay, so I hope that's clear. What we'll do now is step into the demo part of the session. Okay, first I'll take you a little bit through the hardware that we're using. So this is an STM32MP157C DK2. So this is using the hardware accelerated ARM Cortex-A7, so it has a GPU in there. The LCD resolution is 800 by 480, and that's 32-bit. And although it has a touchscreen, we're not using that in this application. It's kind of a display only. In terms of the storyboard side of things, so our runtime is OpenGL based, so we'll be using hardware calls out to the GPU for rendering acceleration, so drawing, blitting, that side of things. The application is a cluster.io. You can see the picture. It's kind of a dashboard type application that may be common on automatic, electric vehicles, or maybe motorbikes or bikes, that side of things. We're going to be looking at how we run this in a storyboard environment first, and then we'll deploy it to the target. So we're looking to use our GAP deployment to Linux over SCP, and I'll show you that. In terms of the hardware platform and the software, we're using the Open ST Linux distribution, which comes from ST. So we've added a few things on there, which is going to be, we've compiled the kernel for enabling LTTNG, which I'll let Christopher talk about in more detail. And we're also going to be using trace points, UST trace points, and these kind of Linux kernel tracing capabilities. Again, Christopher's going to be using Tracealyzer, the Percepio tool, for Linux to analyze this. So we'll be running through this first of all on the desktop environment and then on the target. Okay, so I'll switch over to Storyboard here. So this application is cluster.io. So this is one of the standard samples that ships with Storyboard, and you can do this by doing a file new sample. If I can click on this sample, and then we're going to use a cluster.io. So I've already loaded it, you can see there, but this is using one of our features, Storyboard.io, the API, to basically drive the user interface. So in a bit more detail, there's one screen here. It's a single UI, and there's a bunch of controls and things on here. The speedometer and RPM are particularly interesting in this application. So you can see the way we've implemented this. If I show you the layers there, the speedometer pointer layer has this kind of pointer image, and when we're moving the gauge, all we're doing is changing the rotation angle of that. So we've bound a control to the rotation angle, a control binding. So that's a dynamic parameter we're able to change at runtime. And if I switch over to our events here, so these are some custom events that are going to be exchanged between the front end and the back end. We've got two events here. One is a generic system update. This is kind of a low frequency event. This is more of a status update. So this could be changing things that change less frequently, like the fuel level, the battery, the oil, engine code, and kind of warning lights, indicators, and such. Of course, the distance and odometer. And then we have a second event, which we'll be focusing on mostly, and that's more of a high frequency event. And this would be typically a data extraction being taken from the CAN bus, and these CAN endpoints are being translated into Storyboard format here and sent over the Storyboard IO message mechanism. So we've got two parameters in this one event, speed and RPM, and they're both unsigned integers, 2U1s. So those are going to be arriving asynchronously from the back end. Maybe it's difficult to see, but there's some small arrows on the event definition, and you can see here incoming. This is incoming message as opposed to outgoing. Is going to be arriving from the back end. So the control state machine is going to be sending this event, and it's going to be arriving. At the application level, we have a series of actions, triggers. And these actions are things that basically are defined and are used to trigger events and actions in Storyboard. So Storyboard is an event-driven system. So something, a trigger triggers an action, and an action does something useful. So in this case, these asynchronous event arrivals are going to be calling a Lua function, so a piece of Lua script. And if I show you that. So this Lua script is going to be called every time one of these messages arrives, and it's very simple. Lua is very straightforward languages. We use this for basically doing dynamic behaviors in Storyboard. So this is something that you can't just set a value or set a color or something else. This is something that requires a bit more logic to it. Maybe it's if then else. In this case, we're doing some scaling and translation into numeric and rotation angles. So the data's arriving, we're picking out the speed and RPM, doing some scaling. This is changing the rotation angle. And as you can see here, we're setting both the speedometer and the tacho, setting the rotation angles each time. We're also updating the text value, which is what you see on the screen. So, so imagine the idea that these events have been posted, they arrive, this trigger runs against a Lua function, and the Lua function changes some values, scales it, and this call here is basically setting that data name value pair data set into the render engine, which will trigger a screen update. So it's all very simple. So every time we want to update the data, we're going to call this function. So let me show you how that works in practice. I'm going to hit the simulator button here, but first, before I do that, we've got the ability to I've talked about the Storyboard IO API. So this is the IO data channels. The inbound events are coming through this channel. We're able to simulate that here in the desktop environment. So obviously this isn't connected to real CAN bus hardware, but we're able to simulate these events. So I'm going to be choosing the cluster update event. So that's going to be changing the speed and RPM. So if I now simulate that application, it's going to start up the UI, which you can see here. It's very similar to what we're seeing on the desktop. We've got the pointer angles, but we need to drive them. So what we can do is move this pointer here. We're able to inject those event messages for speed and RPM and simulate the application. Okay, so these events are arriving. It's triggering things. And showing it on the screen. So let me do a little bit more tracing of verbosity first. So I'm going to just increase a couple of things. So these are the simulation settings. So the first thing I'll do is to turn on performance metrics. So this is going to be outputting sort of internal data from Storyboard into a log file. I'm not going to take too much time on this, but I'll show you what we can do from a Storyboard perspective from the inside out. Obviously, when you're running on a target, this is much more system dependent. So we're looking at things outside of Storyboard. This is one process in the entire system. So other system factors, as you'll see later, can influence the behaviors of the UI. But this gives you a Storyboard centric view. So I'm going to put perf.plog here, and this is going to create an event file which is collecting all of the data from startup. what I'm also going to do is increase the trace verbosity here. So we've got a view of what Storyboard is doing as we're running. Okay, so I'm going to run the simulator again. This time we're going to be you can see here we've got trace output, and what we've done now is we've started up the application, and we've got the OpenGL started and various other things. So we're on a screen show at the moment, and if I again I'll pull up the simulator IO connector window, and let's see what happens when I inject some data here. In fact, I'll show you the initial one here. So we can change the odometer values, and you can see here we're actually changing the UI settings, battery levels and such. So that's the low frequency. If we go over to the cluster update, which is just the do data parameters, and I'm going to be changing that. You can see in the trace what's happening is those events are arriving. What we have here is basically the event queue size. So the events arriving, and as we expected, it's going to call our Lua function, CB update event that we were looking at earlier, and that's going to do the calculations and rotations. So we've got the event received, we've got the queue mechanism. Queue is, well, we're waiting to process it for the next frame update, and then the call to the Lua function to actually do that and trigger the update event. So that's a repetitive cycle. So what we if I just stop that down, what we see is also if I flick over to the project view, we've now got a plog file. So what I can do is open this inside of our IDE, and this is basically Storyboard centric logging. Now this of course is on a desktop environment, so it's it's not going to be the same as the target, but it's going to be illustrative. And of course, when you do this on a target, you'll get different numbers, and you can set this on the command line. But on my desktop, obviously, I'm not using very much CPU at all. We can see we're getting some frame counts and updates, average redraw times and such. So this is lots of data that we're looking at, and this is probably the more interesting thing. This is some of the kind of dynamic load on the Storyboard process from an inside out perspective, and you can see here each of these will be when I injected data in, and you can see the changes in load and CPU and such. So this is a very good view for us analyzing our side of the bargain, but obviously when you want to run on a target, it's a little bit more complex. So what I can do here, let me try and do this with a split screen view. So we're now ready there. So we've got our application that was running on our desktop, now running on the target, and let's look at driving that. So one of the things I did is I've got some windows opened up here. So these are SSH terminals to the target, and the application is running on the desktop. So let's just kill that one, and I'll launch it again. Okay, so now you can see the screen is stopped. So we've got two things that we're going to do. So the first thing we're going to do is run our cluster IO. So we're launching the script here with a cluster IO application, and that's going to be running our demo with the trace output. This is from the target, not the desktop in this case. The next thing I'm going to do is simulate the event. So we've got some code here that we've written, and I'll let Christopher go into more detail on that. But this is basically a simple C++ backend with a bit of instrumentation in there, which is calling our Storyboard IO API. And we've taken a second parameter here, which is going to allow us to change the rate at which we're sending. So 80 milliseconds between sends, and if I do that, you'll see the UI moving. So this is effectively updating that pointer at 12 frames per second. So 80 millisecond sample. You can just about see it, but we're getting no queuing. You've got a queue dispatch level of 1. So that means we're processing everything in perspective, in time. So let me kill that back in again. You should see the UI stop. So what happens if we say increase that to something a bit more realistic? Let's go for let's go for 20 milliseconds. So 20 milliseconds between frame updates is going to be 50 frames per second. So this is much more what you'd see. And you can see in the UI, maybe it doesn't come across as fluidly as on the recording as you would in practice, but it is nice and smooth. And we're seeing 2 or 3, so depending on the frame update, we're easily keeping up with the data. And so that's a nice through 50 frames a second. So in reality, you're not going to see anything faster than 50 frames per second. You don't need to send it faster than the display update of the UI, for example. But we often get people asking for, well, can I draw at 300 frames per second? Well, the answer is possibly. Let's look at increasing that now to be maybe a delay of 10 milliseconds, which is a completely pointless 100 frames per second. And the answer is yes, we can draw at that. It looks a bit jerky on my video capture, but it's actually smooth in practice. And we're easily keeping up. Maybe there's 3 or 4 in the queue, so it depends on where the redraw interval is. But yes, you can draw at 100 frames per second. Do you need to? No, because you can't actually see it anymore, and you're just basically loading up the system. So let me stop that again. And let's see what happens where, as we often get, we get customers sometimes setting rather unrealistic targets. So if you set that to 2 milliseconds, we're going to be drawing much faster. And let me show you what happens. And this is sometimes what we get, customers calling in with us and a support. I'm sending all this data. I'm sending at 500 frames a second, and basically it's not working. What's going wrong? You can see there that the base of the UI is, and I've killed the UI here. So the data stopped sending, but it was still basically sending a whole bunch of data into the queue. And you can see what's happening is that if I scroll up, all of these events have been arriving, but we're getting to the point here just about where we're getting into the 800 or 900 queued events. So the data is happening, is being queued into the event queue much faster than you actually need to. So this is really pointless processing. There's no reason to do that level of data update because the display just does not need to show it. So what I want to do now is make use of some of our. I'll do that again, but quickly. And I'll make use of some of our instrumentation we've added that's going to be analyzed in Tracealyzer. So we've got another script which is turning on some LTTNG parameters. Let me kill that for now. So I'm going to run that now, and this runs for 20 seconds each time. So in this case, I'm going to go back and do our 80 milliseconds. So this is our 12 frames per second channel. So that's going to be running, emitting data, moving into the cluster. And you can actually, let me start that again. Start the sequence, sorry again. So I'm going to start the LTTNG trace. That's up and running. I'm going to be starting the front end. That's up and running, and I'm going to be sending the data in. So we're going to be collecting the data tracing going in at 12 frames per second. So that's all fantastic. That should be easily doable on the platform. We're not going to get any performance issues there. So that's saved my traces. I can now stop that and let's move on to the next one. So I'll do that again. So this time I'm going to run it, but I'm going to inject the data at a higher rate. So let's do our 100 frames per second sample here. So first of all, we do 12. This is 100, and we're keeping up quite happily. We're going to be seeing that data arriving. It's going to be queuing up a little bit, and we're going to see the CPU update a little bit faster, hopefully. And finally, let's run the trace again, and let's see what happens when we give it the full 500 milliseconds. So we're going to be really saturating that back end to front end channel. You can see that this UI starts to get all jerky. Basically, these queues are filling up, and there's data arriving, and we're basically discarding the vast majority of that and not displaying it at all. So There we go. So I've captured 3 traces now. I'm going to share those with Christopher, and he's going to do some of those, do some further detailed analysis with that. So if I flick back to my slides now, I'll hand over to Christopher. He's going to take those traces. I've already shared them with him, so these are things we've pre-shared, and we'll look at some of the insights that Tracealyzer can give you by looking at the whole system view. So not just the storyboard centric tracing we saw before, but more from a complete application.
Thanks, Gary. My name is Christopher Martinsson, and I work as field application engineer at Percepio. With Tracealyzer, we can get a broad picture of the behavior of the application at system level and also drill down to see more details. We call it visual trace diagnostics. We support several autos and also Linux. In our Tracealyzer for Linux, we use LTG-NG software trace capabilities for both kernel and user space tracing. The first thing I would like to show is the filters that we have used when Gary captured his traces. So we have enabled all scheduling events to make sure that we can see when different threads and processes are executing. We have also enabled some system call tracing. In our case, we know that the storyboard engine and the driver is communicating over a message queue. So we then select only to trace message send and message receive system calls. We have also enabled some context for our trace events so that we can see the process ID and also the parent process ID, etc. of the different trace events. Our application, the driver, has been instrumented, and we have created some LTT-NG UST trace points, and we need to enable that, and that is what we have done here at the last line here. So here we enable all UST trace events. So let's take a look at Tracealyzer. The trace view is the main view in Tracealyzer. It displays how the different threads and processes are executing in a vertical view. So the time starts here at the top and goes down. The reason for having a vertical view is it's much easier to display the trace messages. As you can see here, the different events here, it's much easier to do in a vertical view. We also do have a horizontal view, but the vertical is the preferred one. Okay, so here we can see when the different threads are executing. So here we see the cluster driver, the driver that sends the data to the storyboard engine. And here we see the storyboard engine, one thread, and actually there are more threads of the storyboard engine here. We can zoom in here to see more details, and let's do that. And now, as you can see, we see a lot of different trace events here. The blue one are a lot of scheduling events when different threads are ready to execute and so on. But here it might be that you are not interested to see everything. And then you can actually filter that by using the filter here to the right. So I will remove some to make it easier to display here. Another feature that is very useful in this view is that since in Linux there are normally a lot of different threads and processes executing, and actually we can see it here. As you can see, there are many threads that has executed here. But we have an auto hide feature here that you can be used so it only displays the threads that are executing in this time frame that we are looking at right now. So what is it that we see here? Yes, here we see a system call entry message send. So the cluster driver is calling this system call and the message send, and then it exits from it here, and it's more or less exit immediately. We can zoom in even more, and actually this can be illustrated by the purple rectangle here, because that's actually the time it took for the system call to complete. And here we see the storyboard engine also making a system call here to message receive, but it doesn't return immediately, and that's most likely for the because the message queue is empty, so it blocks and waits until some data is available in the message queue. So this is the main view, the trace view. You also have the CPU load graph up here to the right. And since this is a dual core CPU, we see both core 0 and 1 in blue and red and green, I mean. And we can see that the total CPU load is at the highest here, somewhere close to the beginning, a little bit above 110%. But we can also go into details about the different cores. For example, here is core 0, and then we can see the different threads when they are executing. So, for example, the storyboard engine, as we can see here, and if I click on it, we can see that at this interval it was executing 30% of the CPU time, but on average, on the complete trace, it was 12%. Okay, so this is the CPU load graph, and actually, you can, of course, you can take a look at core 1 as well. But it does seem to be an issue with the CPU load here, actually. Okay, and there's another view I would like to show you, and that is the user event signal plot, as we can see here. But before we do that, we need to take a look at the event log. The event log contains all the different trace messages that are available in the trace. But we can use some filters here. I have created some user events. As I mentioned before, we have instrumented the code and to output, for example, the speed and the RPM that the driver is actually sending to the storyboard engine. And so, I have already defined that this is a custom user event, so it's visible here. And when I'm doing that, we can take this data and illustrate it in a view like this. This is the user event signal plot. So here we have the RPM here. I can remove that, and we can only look, for example, the speed here. And if I click somewhere or double click here, you will see that it will jump to the same location. And that is true for all views. So if I double click somewhere, it will jump to the same location in the trace in another view. So all the views are synchronized. So this was just a quick introduction here, and I've been using one of the traces that Gary has recorded. So let's take a look at one of the other traces. Let's open the trace with a 2 millisecond delay, or with an update rate of 500 times per second. So let's open that. And actually, if we look at the CPU load graph, it's not a huge difference here actually. If I just take a look at the storyboard engine here, as you can see, the CPU load is on average 70%, so just slightly higher than on the other trace that we recorded. But more interesting is actually to check the system call plot here. The system call plot shows the system call and execution time of the system call. And the response time here, what that means is that is the total time from entry to exit of this system call. So in this case, I'm looking at the message send that is called from the driver. And if we look here in the beginning of the trace, we can see that the time is very, very low. It's just on microsecond level. So I can double click it here, and actually we can zoom in here. And we should be able to see that this is roughly 32 microsecond in this case, the execution or the response time of the system call. But then after a while here, we can see that the response time has increased a lot. So let's double click on one of them. And as you can see now, it's zoomed to the same location, and now we need to zoom out a little bit. But what we can see here is that we have a system call entry message send, but it doesn't exit immediately. So let's zoom out a little bit more here. And actually I can click here, and when I do, I see this rectangle here, and that actually is showing me all the way down to when this actually returns. Well, I need to zoom out a little bit more here, like that. And here it returns. And we can see we have the exit here. So what's going on here? And actually, by just looking here in the trace view, we can see that, okay, it did call this system call, but then it blocks, and most likely it blocks because the queue is full. And actually that we can see here, verify, because here just above here we see a message receive here in the SP engine thread. So, and just after that, the system called the message send returns. So that is the reason in this case. And we can also see this in the event log. If I filter this and search for all MSG like this, and if we look in the beginning of the trace here, we can see that here the cluster driver or the driver sends a lot of stuff to the queue, and then the SP engine storyboard engine, it's consumes a few of one of these messages here, and then a lot of more messages is written, etc. So we are writing way more than the storyboard engine can handle. And finally, if we scroll down here in the event log a little bit, you will notice that suddenly there is only 2 send and 2 receive here, and that is when the queue is full, because then the message send will need to wait here. So there is for sure no reason to send more data more often than the storyboard engine can handle, and we can spot it quite easily here in Tracealyzer. So that was all I wanted to show when it comes to Tracealyzer for Linux. There's a lot more that you can do with this tool, but we don't have time to go through it all. So I will hand over back to Scott.
Thank you very much. So just before we jump into the Q&A, I just want to kind of wrap things up. Definitely, as I mentioned at the top of the hour, that the user experience has really become that defining part of the embedded products that consumers, or is driving consumers' expectation and the value they see on the product. So definitely, you know, making sure that you provide the best user experience possible is critical. So definitely, you know, to achieve the best performance and power figures at any time, leverage that power of the STM32MP1. And you can use this link to take you into ST's kind of website on the portal on the STM32MP1 to learn more about it. Also, check out Tracealyzer to gain that amazing insight into what's going on within your runtime system, or more particularly within the GUI application. So that way, you know, if you need to then go back into Storyboard to make those modifications to make sure that the experience has been fully optimized for the user and for the hardware. And last but not least, we have free trial software of Storyboard. It's a full featured version of it that you can download, leverage all the great aspects of it. We also have demo images for the STM32MP1, so that way you can check out the graphical performance of the board before you even developing yourself, as well as we got a variety of onboarding and getting started videos to really make the development process that much more easier for you when it comes to leveraging Storyboard. So with that being said, I'm going to jump over into your questions. All right. So the first one is, will these presentation slides be available as a PDF? Yeah, so one of the things when we do the follow-up to thank you and provide you with the link to today's session, we will be sending out a PDF version. How does Storyboard use standard Lua or Lua JIT? Gary, this one would be for you.
Yeah, thanks, Scott. Well, Lua is part of our framework. It's part of our plugin. We have a plugin for Lua. It runs on all platforms, even the MCU ones, and this is really part of our engine and not part of the operating system. So the scripts that we write are either stored and interpreted from the Lua script, or you can pre-compile them. So they get turned into kind of intermediate code, and we run those with a mini interpreter, really. So the Lua engine is built into our runtime. So yeah, we have a link with our Storyboard API, and we've extended Lua language to add some extra function calls in there, which drive the UI itself. So it's really pretty straightforward. I encourage you to give it a try.
Perfect. The next one seems to be maybe an open one for either Gary or maybe Mike, a bit of both. What display device can I use? Can I use an iPhone? Can I use an Android-based device?
We were showing Linux today. So Storyboard does write or create packages for Android and also iOS. Mike, I'm not sure if Android is available for the MP1. Maybe
yeah,
not.
so we have we have both Linux and Android packages available. You can go to wiki.st.com and explore both of them. In terms of the display devices, the MP1 supports LCDs. So whether it's a parallel LCD, a TFT LCD, or a MIPI DSI, that's your choice based on your hardware design.
Perfect, thanks. And the next one's a little bit of a kind of both Gary and Mike one as well. So it says this may have been addressed, but will this run on the STM32H750, or what resources must a device have to leverage this? So it's a two-parter. I'll start with that one. And yes, the beautiful thing, like I mentioned when I was talking about Storyboard, is that it is agnostic in the sense that it can easily scale from the MP1 down to the H7 series from STMicroelectronics easily. And the beautiful thing, like I said, is that you could easily develop on one and take that UI and have that portability to have it work on the other. So whether you're scaling down or whether you're scaling up, in particular, depending on what your embedded product is, if you have a range from maybe a low end to a high end, where you want to have maybe cost effectiveness versus rich 3D graphics, you could easily use Storyboard to build the UIs across that and reuse that UI across that with maybe some enhancements for the 3D or to make it more optimized for the hardware easily using Storyboard. The second part of the question, this seems similar to TouchGFX. Is this a replacement, an enhancement, or an alternative to that workflow? And Mike, I'll let you start on that one.
No problem. Yeah, Mike Hartman here from ST. So I would say on the microcontroller side, yeah, it's you can use TouchGFX or you can use Crank. TouchGFX is ST's free graphics framework option, but Crank brings a lot more, as well as that scalability that Scott mentioned. So I know Crank also offers services which aren't included in some of the free offerings out there. But the scalability is really something that I think can be driven home, because TouchGFX is purely for the STM32 microcontrollers and does not run on the MP1. And so, what we showed today was purely based on the MP1. So, Crank is a great option there.
Yeah, so just to kind of build upon what Mike is saying is that definitely, and not to downplay ST's kind of product, you do have that product to be able to free for you. Great for prototyping, great for getting that kind of that experience going on the MCU products. But if your product has a need to go outside the MCU into the MPU space, that's maybe where you would need to start looking at alternatives, and that's really where Storyboard comes to the table because, like we said, you can easily scale up or scale down. So if you start to the MPU, go to the MCU, or vice versa. Plus the fact that we just recently released our latest version 7 of the software, which we've actually did a lot of extra stuff in there for the MCU space, in particular maybe for the wearable space, to provide some low code to no code options to really develop some real powerful, sophisticated embedded UIs for those devices a lot more easily, a lot more efficiently by, instead of having to code out, say, for example, scrolling tables, click of a button, and you have that option there available for you. So we are constantly innovating with it and constantly providing you with different capabilities and feature enhancements. Like I said, the top of the hour was our rapid design and iteration technology, which allows you to work with a design firm. They can build out that UI design within Photoshop or within Sketch, then easily import those design files, whether the initial ones or change the design files, really allowing you then kind of to iterate on the design, because as I like to say, it's not a matter of if, it's a matter of when those iterations are going to occur, because when you have a group of people that are working together on a product, when you start going out there and soliciting feedback, everybody has an opinion. And so really Storyboard really makes it easier and more efficient to adopt those changes easily into the design, to really make sure that UX is fine-tuned for the end user themselves. So with that being said, now's your chance to get any other questions that you may have for us, for the panelists today. I'll give it a little bit. I know we ran a little bit over, but there's a lot of great information that Gary and Christopher were providing with the live demo. But as I said, this will be made available to you. And we will provide you with the PDF format of the PowerPoint. So if there's no more further questions, I want to thank you for sticking around, and I want to thank you for taking time out of your day to come let us talk to you. Thank you very much. Talk to you soon.